Okay, stoichiometry by analysis is different from regular stoichiometry because you might not know the formula of the substance you are burning or analyzing or decomposing. Your goal is actually to figure out the formula. And so in this example, we do not have the formula for acetyl salicylic acid. We know it has hydrogen, carbon, and oxygen in it. This means that we can't use coefficients. We can't use mole ratios and coefficients. We'll have to rely entirely on mass. And remember, we have percent by mass to really help us when we need to rely on mass. Okay, the first part of this problem I think is pretty easy. It's really just 0.325 is the grams of the active ingredient. Divide that by the overall 2 grams, times it by 100, and you'll get the mass percent. We're going to be really working on this second part. Imagine the combustion of this. They tell me it contains hydrogen, carbon, and oxygen. I do not know in what ratio. And we're going to burn it. I know what that reaction looks like. I know it produces H2O and CO2. Remember, this doesn't have a right formula, so we do not have correct coefficients. I'm really just sketching this out to see where my elements end up. Specifically, they tell me I'm going to start with 3.000 grams of this whole compound. My hydrogen, all my hydrogen, ends up in the water. They tell me the mass of the water, 1.200 grams. So I can use a percent by mass to pull the mass of hydrogen out of this. I can also see that all my carbon ends up in the carbon dioxide. They're telling me I have 3.72 liters of it, and I'm going to adjust this just a little bit. I'm going to say this is STP. It is so close that it's going to work out, and we're going to change that in class to STP. Okay, so can I use my fact about a mole of gas here to figure out moles of carbon, to figure out grams of carbon, and trace it back into there? Absolutely. So that's the path my carbon takes. That's the path the hydrogen takes. Okay, let's look at the hydrogen. In water, it's always 2 hydrogens for every water. There's always a certain percent by mass of hydrogen in water. It turns out to be about 11%. If I want to do it in one step, it looks like this. Here's my mass of water. If I put the mass of 2 hydrogens on top and the mass of water on the bottom from the periodic table, this is like my percent by mass of hydrogen in water. So 2 hydrogens, 1.0079 times 2. And then the whole water. Okay. If I do it this way, you'll see that the grams of water cancel out. I'll be left with grams of hydrogen. If you do this, essentially you'll see that this here is 0.1119, which is 11.19% hydrogen by mass. That will always be true of water. And I can always figure it out by doing 2 hydrogens over the whole water. Okay, this gets me 0.1343 grams of hydrogen to 4 sig figs. And remember, all that hydrogen came from here. So this is my total. And I know 0.1343 grams of it is hydrogen. I'm like halfway there. Okay, let's pull out the carbon and do this work over here. 3.72 liters of carbon dioxide. If I'm at STP, then 22.4 liters of any gas will be 1 mole of that gas. Now before I punch this out, notice there's only 1 carbon in each molecule of carbon dioxide. So, if I want to focus on just the carbon, for every 1 mole of carbon dioxide. It is 1 mole of carbon. And I even want masses, right? My liters will cancel. My moles of carbon dioxide will cancel. If I use the molar mass of carbon here, I can do this all in one step. Carbon weighs 12.011 grams per mole. And this math will get me my grams of carbon. And all the carbon came from the acetyl salicylic acid. Okay, I got 1.99 grams of carbon. To 3 sig figs, because this guy's 3 sig figs. And remember, all of that came from here, 1.99 grams of carbon. I figured out 2 of my elements, and I know my total. Let's just subtract, and I'll have the oxygen. This guy only goes 2 places past the decimal, so my grams of oxygen will only be able to go 2 places past the decimal. So 0.8, it's going to round up to 0.88 grams of oxygen were originally in this compound. Okay. Now that gets me the answer, the mass in grams of each element in the 3-gram sample. I want to point out though that I could then use these masses to try and figure out the empirical formula. I would take these masses, I would turn them all into moles using their molar masses, and then I would try to find the simplest mole ratio. This might not be that easy with something like acetyl salicylic acid, but let's see what happens. Okay? Let's see. Point 1343 grams of hydrogen. 1.99 grams of carbon, and 0.88 grams of oxygen. For now, I'm going to keep a lot more than I need here, 2, 4, 7, just to try and manipulate this ratio a bit. This would get me about a 1 for the oxygen. About a 3 for the carbon. And a 2.4 for the hydrogen. You know what I like for this? I like 5 to 6 to 2 for simple ratios. I suspect it's something larger than that, but it is, after all, an empirical formula, which is the simplified version. Okay.